Okay, this video is on linear functions. Up to now we've been talking about functions in general. Now we're going to talk about a specific class of functions called linear functions. And the first thing we're going to ask is, if I have a graph right here, this kind of curvy graph, and I ask, is this the graph of a function? Well, right away I can say, yes, I know this is the graph of a function because I can see that it's going to pass the vertical line test. Anywhere I draw a vertical line, it's only going to hit my graph in one place, therefore it's a function. Now, if I ask the question, is this the graph of a linear function? Well, the answer to this question is going to be no. I can tell that this graph is going to be the graph of a function because it passes the vertical line test. But just because a graph is the graph of a function doesn't necessarily mean it's the graph of a linear function. You can tell a graph is the graph of a linear function if the graph is a line. That's where the word linear comes from. It comes from line, L-I-N-E, line. Line and linear, and since this graph here is not a line but is instead a curve, I can tell that even though it's a function, it's not a linear function. So this distinction between a function and a linear function is fairly easy to determine if you have a graph of your function. You just look at it and you decide, is this the graph of a line? Well, if you don't have a graph, then you're going to have to use something else. A function that has the same average rate of change on every interval has a graph which is a line and is therefore a linear function. So let's take a look at an example where we're going to see this average rate of change, this constant average rate of change. Example number 1. It says a town of 30,000 people grows by 2,000 people every year. Since the population is changing at the same rate every year, it's going up by 2,000 people every year, then I know that P, my population, is a linear function of time. That's what a linear function means. It means that it has the same average rate of change over every time interval. So part A here says, what is the average rate of change of the population over every time interval? Well, I'm told the rate of change of the population is 2,000 people. In other words, the population is increasing by 2,000 people per year. So that's my average rate of change. Part B says, make a table that gives the town's population every year over a 5-year period and then graph the population. So I'm going to make a table here, and I'm going to do my graph over here. My table, I want a table that gives the town's population every year over a 5-year period. So here I've got my table. I'm going to put my independent variable, which is t, in this top row. That's my independent variable. I'm going to put my dependent variable in the bottom row. That's my population. And then I want the population every year over a 5-year period. So I'm going to start with time t equals 0 when my population is 30,000. 30,000, and then I'm going to have it for every year, 3, 4, and 5 years after that. So if I start at time 0 with a population of 30,000, my population is growing by 2,000 people every year, so that means after 1 year I'm going to have 32,000 people, the next year I'm going to have 34,000, then 36,000, then 38,000, and then 40,000. All right, so here's my table. It gives the town's population. Now I want to graph this on this set of axes over here. So my independent variable is t. So here's going to be my horizontal axis, t for time. And my dependent variable is p for population. So that's going to be my vertical axis here. So let's see, time t, I'm going to go from 0 to 5. Here's my time t is 0. There's 1, 2, 3, 4, 5 years. At time t equals 0, my population is 30,000. So let's say, let me just start right here with 30,000. And I don't know how far up that's going to go. Let me put a couple of lines in here to indicate a break in my vertical axis. So 30,000 at year 30,000 at year 0. So I'm going to have a point right here on my graph that represents this point. At year 1, my population is 32,000. So let's see, let's do this. 30, 32, 34, 36, 38, and 40K. So at year 1, I'm at 32K. Year 2, 34. Year 3, 36. Year 4, 38. And year 5, 40. So there's a graph of my population over this 5-year period. And you can see that these points, they do appear to lie on a line. All right, part C, find an equation for P as a function of T. So I'm saying that my population is a function of time, and I can write P equals F of T. Notice, however, this is not an equation for my function. This is just notation, right? In fact, we call this basic function notation. Well, I don't just want function notation, I want an actual equation, which means I'm going to need some actual numbers here that describe this function, that describe this relationship of the town's population over time. So I want to say my population is going to equal to something, and it's going to be a function of time, so t is going to show up as a variable in my equation. Well, since I know that my population starts out at 30,000 people, and it goes up by 2,000 every year, I can write this equation, I can model the population of my town as 30,000 plus 2,000 people every year. So if I say 2,000 times t, then when t equals 0, my population is going to be 30,000 plus 2,000 times 0, which is 30,000. At t equals 1, 30,000 plus 2,000 times 1, that gives me 32,000, and so on. So here is my population, or excuse me, here's my equation for my population as a function of time. Now, I can always tell that an equation is a linear function if it has a form that looks like this: y equals mx plus b. And hopefully this looks familiar to you. This is a common form of the equation of a line. It's called the slope-intercept form. Slope-intercept form. And it's called the slope-intercept form because if you have the slope and you have the y-intercept, then you can write the equation of your line. And so here, let's just go ahead and identify each one of the pieces of this equation. This is my dependent variable. This is the slope, or we could say average rate of change. This is my independent variable. And this is my vertical intercept, or you also hear this called the y-intercept. We're going to call it the vertical intercept in general because sometimes we're going to have equations where the dependent variable is not necessarily y, so we just call this the vertical intercept. That's where my graph is going to intercept the vertical axis on the set of axes. Now, parameters. Parameters are just values that define a function. So when we're talking about linear functions in particular, the parameters that define a linear function are the slope or the average rate of change, and the vertical intercept. In other words, if I know the slope and the vertical intercept for a linear function, then I have completely defined that function. If you tell me what the slope and the vertical intercept of a linear function are, then you've told me everything that I need to know about that function. Okay, example number 2. How can we tell if the data in these two tables represent a linear function or not? Well, if I had been given these functions as graphs, then it would have been fairly straightforward. If the graphs were straight lines, I would know they were a linear function. If they weren't straight lines, I could say, no, they're not a linear function. Well, I don't have a graph, I just have these data points. I have individual x, y data points. So what I'm going to have to do instead is I'm going to have to use the fact that I know a linear function must have a constant rate of change over every interval. In other words, I know that delta y over delta x, which is the rate of change, this number has got to be constant over every interval. Well, let's take a look at delta y over delta x for each one of these functions and see if they're constant over every interval. So I've got my x values in the top here, my independent variable, and I've got my y values, or my dependent variable, in the bottom. So let's calculate all our delta x's and our delta y's. So delta x just means the change in the x value from one point to the next. So from 50 to 55, that's going to be plus 5. 55 to 60, that delta x is going to be also plus 5. 60 to 65, plus 5, and this is plus 5. My delta y's, I want the change from 0.10 to 0.11. That's 0.01, and this is 0.01, and this is 0.01, and 0.13 to 0.14, that's also 0.01. So it's not too hard to see with these numbers that delta y over delta x, for any pair of points that I choose here, my delta y over delta x value, delta y is always going to be 0.01, and delta x is always going to be 5, which means that my delta y over delta x, it's always going to be constant, and that's whether I use this pair of points here or I can use this pair of points over here. That's also going to give me 0.01 over 5. Therefore, since delta y over delta x is constant over every interval, I know that this function must be a linear function. So let's take a look at this function here in part B. Is this a linear function? Well, I'm going to do the same thing. I'm going to calculate my delta x's and delta y's and then see if my delta y over delta x value is going to be constant over every interval. All right, so I can see all of my delta x's are going to be the same as they were before. They're all going to be plus 5. And let's see, my delta y's, this one is going to be 0.02. This one is going to be 0.03. And now right away I can see I've got a problem with the linear aspect of this function, because if I calculate delta y over delta x for this set of points here, then my delta y value is going to be 0.02, and my delta x value is going to be 5. If I calculate delta y over delta x for this pair of points here, then delta y is going to be 0.03 over 5. And I can see right away these two values are not the same. And since these two values are not the same, my delta y delta x is not constant over every interval of this function. Therefore, this is not a linear function.